Welcome to this final week of our focus on the family Myrtaceae. Our understanding of Myrtaceae and its lineages are changing every day. With widespread access to genetic sequencing technologies and new fossil discoveries, genera are constantly being redefined, renamed, and reorganized on the Tree of Life. Just this semester, I found out a plant I'd been trying to ID since May last year wasn't a Leptospermum at all, but a species of Gordium. But of course, up until a few years ago, my first assumption would have been right. But that's not why we're here today. In weeks 9 to 12, we discussed Asteraceae, Apiaceae, Orchidaceae, and the monocots, both lily-like and grass-like. These plants give us insights into the evolution of angiosperms, especially into the age of mammals through the Cenozoic, and represent a major shift in available food sources. Myrtaceae too represents an interesting development for herbivores. Eucalypts in particular became ubiquitous throughout the Gondwanan forests. Being everywhere in endless forms, we'd expect everything to be eating them given the chance. But in actual fact, consumers of Eucalypts, Syzygium, and other Myrtaceae often have to evolve close specialisms to be able to withstand and metabolize the plant's defenses. Koalas, of course, are the classic example, having to spend most of their day digesting for negligible energy profit and consuming their mother's scat for the right gut flora to do so. But the main predators of eucalypts tend to be insects. This year, a fossil Pergidae sawfly was described and analysed against its host plant, suggesting that the adaptations needed for eucalypts to be a primary larval food source could have occurred independently at least 4 times in this lineage. Sawfly diversification also coincided with Myrtaceae radiations through evolutionary time, with different subfamilies of sawfly specializing on different Myrtaceae genera. An especially interesting detail is that members of this group can either avoid the plant's toxins through careful feeding behaviors, as we saw with Asteraceae's latex, or separate the toxins from food using mouthparts or enzymes. Some can even recycle these toxins as a defense mechanism, vomiting the stored oils at their own predators. Eucalyptus in particular presents as an excellent model to study the evolutionary arms race between plants and their predators through geological time, with loads of living species and diversity, coupled with a comparatively long fossil history from the Eocene of Patagonia to today, and its dominance in Australian landscapes through the ages. Comparing the patterns of insect leaf damage from living specimens to those found in the fossil record, you can see a range of types of feeding mechanisms and responses, including galls and mines, and follow the progression of ecological relationships in a way you seldom can with other fossil lineages. Through this fossil record, it's also possible to follow the development of quintessential Myrtaceae traits, especially concerning its woody fruits, leaf morphologies, and pollen, where pollen can also indicate when and whereabouts lineages lived as continents and climates shifted. As well as restructuring extant phylogenies, recent research is also beginning to uncover unexpected relationships between eucalypts as major biome builders before and beyond their evolution alongside fire. New research from India this year described insanely well-preserved fossil remains of both the vegetative and reproductive structures of an Eocene eucalypt. Judging from the floral and vegetation morphology, researchers have been able to place this species close to Eucalyptus itself in a phylogeny also supported by molecular data. While objectively awesome, being able to describe a fossil species doesn't really get us closer to understanding how and why our iconic gum trees evolved. This is where ecosystem-level evolutionary research comes in. As we discussed in the rest of this series, the ability to withstand frequent disturbance and competitive interactions affords plants significant power over their environment. Today, ecosystems are often classified based on their dominant or keystone plant species, which can in turn tell us a lot about the kinds of selection pressures these systems operate under. But what if we were to look further back in time? Would we recognize their past evolutionary selves before familiar conditions shaped them into what we know today? That's the question Wilfred Krugman posed in New Phytologist while discussing the problem of rainforest edges, Myrtaceae's long prehistory as a rainforest plant, and how we manage different ecosystems. According to their review of the existing research, early eucalypts were rainforests or adjacent species, and expert opportunists when it came to soils freshly exposed by disturbances. The deficit of charcoal at most fossil sites pre-Pliocene suggests that fire only came into prominence in eucalypt-dominated systems recently, meaning that their epicormic buds and fire affinity is something exacted from their prior affinity for quick succession after volcanic and geological disturbances. Given the tug-of-war between rainforest and eucalypts evident through prehistory, it's very likely that these abutting ecosystems co-evolved as balances for each other, which is absolutely fascinating. So we know that every member of this family has its ecological niche, with preferred temperature ranges, rainfall, and disturbance regimes. But what about the world of tomorrow? Microevolution, that is, change across single lifetime timescales, is possible, but unlikely to allow Myrtaceae to adapt to the unpredictability of climate change fast enough to avoid significant extinctions. To understand how Myrtaceous biomes and their species will be affected, we'll need to understand how they tick and why they disappear. New ecological theories, like the alternative biome states, may provide crucial insights into how ecosystems change between climate and geographical conditions. But we also need to recognize that the line between ecosystems is often blurred in landscapes, and that even tiny patches of similar but different ecosystems inevitably support unique organisms that deserve our protection and conservation, irrespective of how undesirable, inconvenient, or unimportant they might seem to humanity. It's a confronting thing to end on, both for this semester and this series, so instead I'll leave you with this thought.